Yeah, so he attached it to his computer, so every time he turned on his computer, he would have to see his video. Oh, yeah.
Welcome to JPL. My name's Brian. We got Curtis, we got Mark, we got Nick. We're all your guys. Before we begin, I know we're in 3 separate groups right now. We're going to start together. But before we do, can I get your attention, folks? If you're with us, you know us. All right, great. If you're with us, come on over a little further this way. Yeah, you guys. Yeah, I'm talking to you. You're wearing a badge and it says tour. You're with me. So welcome. Before we begin, a couple of very important rules, though. First off, we're going to stick to one side of the sidewalk. So we're all going to be on that side right over there. You guys will catch up when we walk through. It's a working facility. We need to make sure that people can get on and off lab without us getting in the way. We're going to do that the best as we can today. Also, we're going to keep our voices down. Being a working facility, we don't want to be the reason anybody puts a decimal point in the wrong spot. So we'll just keep our voices down everywhere we go. We're going to walk everywhere we go, as tempting as it's going to be to run, to jump, to climb, to parkour, to use your Jedi mind tricks or your magical wizardry powers, anything like that. We just ask that you walk everywhere we go. We'll have a great time. Nobody trips, falls, hurts himself. Stay together as a group. Take all the photos that you like. Yay, photos, woo! If you do video, though, I ask you keep it shorter. Snapchat in length. If you don't know what that means, ask one of the kids standing around you. But go ahead and follow me right this way.
Sesim geliyor mu acaba? Evet, şimdi uzay araçlarının maketlerinin olduğu yere gidiyoruz. Maketleri değil de ikizleri. İkizlerinin olduğu yere gidiyoruz. İkizlerini tekrar yapıyorlar çünkü bir problem çıktığında üzerinde çalışmak için. Voyager. Bu plan içerisinde Türkçe bir ses var. Sabah şerifleriniz hayırlı olsun diyor. Juno.
Now we can fill in both sides. Fill in whatever you want from both sides. That point. So if you see a seat at this point, go ahead and take it. Like getting on an airplane, you think you're going to have a baggage red thing, and it turns out there's not. Hi everybody. So now that I'm not shouting at you in a circle, my name's Brian. It's got this mark in the back. Nick's the first walking around today. So who has heard of JPL before? Who got thrown into a car and said, hey, we're going on a trip? Always one. Who can tell me what JPL stands for?
Jet Propulsion Laboratory.
Very nice. So we're part of a much larger organization, which is what? And what does NASA stand for? Yes. One person over here who wants to know, everybody know he's smarter than all of us. They got it in there faster than anybody else. National Aeronautics Space Administration. On the nose, yes. Usually when it's left to the group, it goes National Aeronautics Space Administration. Goes in the sky, goes up to space. It's non-military. We build it, we launch it, we monitor it, we do all that kind of stuff. It happens with NASA. Now we're one of 10 NASA centers. We're the only one that is an FFRDC. What does that mean? That means the chairs belong to NASA, the podium belongs to NASA, but we, the people, we work for Caltech. So all of us will see a nice little Caltech JPL on our shirts. NASA gives the money to Caltech, Caltech runs JPL. You might have heard of some of the other centers. You might have heard of Kennedy Space Center, most of them launching there. Johnson Space Center in Houston, over here with manned space flight. Houston, we have a problem. People have to throw that one back in our faces. Astronauts work there, they train there. The thing that goes round and round, the pretty cool well, that happens from Houston. Here, we are the leading center for unpersoned exploration of the solar system. What's that mean? Robots, rovers. We send robots to cool places and do things that people can't do yet. We're going to talk about why that's important in a little bit, but I want to give you a brief history of this place because you all can't do this. Wonderful place, got a lot of history here. Way back in the 1930s, a couple of amateur rocket enthusiasts were developing rocket propellant in their backyard here in Pasadena. If you've ever tried to create rocket propellant, you know it's not very safe or stable to do. Lots of explosions, lots of potholes, not a lot of rocketry was actually happening. So their names were Jack Parson and then Foreman. Parsons was the chemist, he could make the things go boom. Foreman was the welder, he could make the vessels for the things to go boom in. They weren't having a whole lot of success, so they came over to Caltech, about 6 miles away from where the crow flies. Now listen to a lecture by Dr. Theodore von Karman. An idea of how important Dr. von Karman was. Right now you're sitting in the von Karman auditorium. So very important guy, visionary, very smart. He was doing a lot of work with the military, and he had a, basically, he was giving this lecture about the future of aviation. This possibility, this pattern, this maybe, could we, I think we can, maybe at some point, go to space. He really liked their enthusiasm because they talked to him afterwards, but they were amateur rock enthusiasts. And once again, sir, if you're doing video, we ask you to keep it to short, 10 seconds, 15 seconds, and doing your stuff. So he introduced one of his students named Frank Molina. Now, Frank Molina and Parsons and Foreman, they became what was known around campus as the Suicide Squad. This is before the Will Smith movie, Margot Robbie, anything like that. Before the comic book, it was a group of students at Caltech campus trying to create rocket propellant. Lots of explosions, more potholes, and fumes. If you've ever tried to do that, lots of fumes come out. A couple stories in particular where they earned their name. Foreman and Parsons were doing something. Molina had to talk to the guys. He had to go deliver a typewriter. 2 minutes after he left, 2 minutes, there was an explosion. One of the gauges from the instruments went right into the wall, right where his head was, 2 minutes later. They built this huge pendulum to test the power of the engine. The power of the engine, how far and how fast it rolled. It spun, it waved, with how powerful the engine was going to be. Gas leak, anything that was metal or shiny or polished, rusted immediately. And Caltech said, you don't have to stop what you're doing, just please move outside. So they moved outside, built the same contraption right next to the building, the whole thing crashed and collapsed. And Caltech said, you don't have to stop what you're doing, just please move off campus. Came up here to the realistic of where you want to go. They drove up here, some people took buses, some people took Ubers, in the middle of nowhere, right? And these buildings burn around. Back in the 1930s, it was a whole different world. They had to lug their equipment back and forth 6 miles from California up here to the Erosi, because it was a dry riverbed. It was also prone to flash flooding. And we like to say that we were officially founded on Halloween of 1936. Why that day? That was the first day that nothing blew up. In the experiment, we had our engine aimed down. The jet burned up for 13 seconds. That was it. Holy moly is right. That was it. And we were officially founded that day. And those of you doing the math in your head, we are 36, or not 36, 2036, we were 80 years old. So we've been doing some sort of that since that point. But we were, well, the reason that we're the Jet Propulsion Laboratory, we're not the Rocketry Laboratory back in the 1930s, if you use the phrase rocketry, you could be laughed out of a room by the generals, by the Pentagon. They were thinking of Buck Rogers flying around in the radio trying to save the galaxy. They weren't thinking about something you could actually do, actually take it into space. But the phrase jet propulsion, ooh, that's a buzz phrase. Generals love that. It's the same thing. At the back of your rocket, you have a jet. That jet propels your rocket, jet propulsion. And they put it in a proposal about jet-assisted takeoff. Anybody familiar with jet-assisted takeoff? Okay, a couple of people. Anybody familiar with the Blue Angels? Yes, they take off right off to the front, right away. Like the jet assisted takeoff, jet assisted JTO rockets were developed here at JPL. We also worked on powerful private stars and missiles. And then in 1957, the Soviet Union threw something up in space. Anybody know what that was called? Sputnik. That's right, Sputnik. Or Sputnik, which means fellow traveler in Russian. And the United States said, hey, we should probably get one of those too. Sputnik was just going around the world beeping a lot and making people very nervous. You could hear it on the radio. So Vanguard was given the approval. Vanguard was given the approval over us. It was a very close vote. But Vanguard was mostly non-military, and we were still working heavily with the Army. President Eisenhower, at the time, had some qualms. He had some worries, because nobody knew where airspace ended, where air rights ended. So going all the way out, even out of the atmosphere, does that belong to? So by sending a non-military satellite up there first, you can kind of alleviate those worries and fears. However, unfortunately for Vanguard got about 2 feet off the ground, and not a good day for us, the United States space program. But it's an okay day for us because we got the approval to do Explorer 1. So 90 days later, we had Explorer 1 ready to go and launch. We walked right by a model, a full-scale model of Explorer 1. It's the first U.S. satellite. What makes it so cool? We worked with the team in Redstone, the Alabama team. We also worked with Dr. Van Allen. Dr. Van Allen, what makes it not just a U.S. first, but a human first, is the first science platform launched from space. Dr. Van Allen from the University of Iowa put a Geiger counter on a particle detector, and we discovered the Van Allen radiation gas. All that happened here at JPL. So we were the first to do that. That was in 1958. Later in 1958, you ready for this? Well, later in 1958, Congress passed the Space Act. And who's read the Space Act? I recommend you do, especially now. Go back and read it. The Space Act is about the formation of NASA, why we were created as an agency, as an administration. The very beginning, this is in 1958, this is the height of the Cold War, Formation of NASA is about the betterment of all mankind. Not the United States military, not the United States, all mankind. This was at the height of the Cold War that we wrote this down. And Dr. Pickering, who was the director of the lab at the time, he thought it was odd that an educational institution, Caltech, was still working with the military. December 1st, 1958, we joined with NASA. We've been working with NASA ever since. We were older than NASA, and we're the leading center for unpeople or robotic exploration of the solar system. So why do we send robots out there first? To test if it's safe for humans. Yes. What else we got? What you got, man? Yeah. You got an answer. No, Google. No, what's the Google?
Robots don't need to eat or breathe.
Robots don't need to eat or breathe. On the nose. On this side of it. Okay? Why are robots cool? You don't know? Well, hopefully you know by the end of the time. Hope you have some reason. They can control them remotely, yes. They can take pictures much quicker than we can. As much as you think you're just yourself, you're much better. Much more safe, yeah. Anybody know how long it took to send somebody to the moon, from launch to the moon?
It was like 13 days.
3 to 4 days. The whole mission was about 13, 14 days, yeah. So about 3 to 4 days up there, 2 people went on the moon, 1 person felt very jealous, orbiting around, and they came back home. Anybody know about how long it takes? And we have to send, we're at a point, we have to send food, water, oxygen, shelter, all that good stuff, going up to the moon and back. About how long it takes to get to Mars. Anybody know that? Yeah, between 6 to 9 months, depending on that orbital ballet around the sun. So if you're going to be sending a person up there, you're going to be sending food, water, oxygen, shelter, all that great stuff up to Mars. And then once you're on Mars, you have to be there for another 1.5 years, because we can't launch to Mars. We can only launch to Mars for 26 months, because it's in that orbital ballet around the sun. It takes that long to get there and back. And also, we like to bring our astronauts home. Big thing we like to do here at NASA. Much like how Dan and Chagrin, we like to bring people back. So, we don't have a rocket right now big enough to take the rocket there that's going to bring them back home. Curiosity, the rovers, anybody familiar with that? Big view with. Been up there for 4 years. Voyager 1, Voyager 2. I'll talk about it more after this video. They've been out there for 39 years. 39 years. How old are you? 11. Well, however old you are. Either way, it's a quarter of how long it's still communicating with the thing. We'll talk about how and why and all these great things. Why it's still important, why we're doing things. A couple of the rules to once again, just walk everywhere we go, more of a line, no parkour, nothing like that. As tempting as it's going to be, we'll probably split up into 2 smaller groups. If anybody needs to use the restroom, don't just wander off, tell one of the tour guides. Otherwise, we will leave, and our officers have to come and find you. And while they are perfectly lovely people, not when they have to hunt people down, much rather stay with us for very fun. Ask all the questions you want. And if I don't know the answer, I'm going to ask somebody else. If they don't know the answer, I'm going to ask somebody else. If they don't know, we'll go to the Google machine like you just did there. But I want you guys to know that sometimes the questions are more important than the answers. And I'm going to be the first person to tell you I don't know. Hopefully you teach me something today because of that. That's not just for the students, that is also for the adults. I'll point that out. It's okay to say I don't know as long as you're willing to find out. Sometimes making it till you make it's okay, but not today. Don't do that here. Take all the photos you like. Video, we have to keep it short at each stop. Just take like 10 to 15 seconds of video at each stop. You don't want the whole thing ending up on YouTube because then we're all on the job. People don't even come here for. And look where you are right now. Have a good time. There might be wildlife coming out. If there is a deer or something, don't just shout and go deer, because they're wild animals. They will do what wild animals do. They will run off, and sometimes they will run at us. They'd rather just be very quiet when we see them. Give me a second. I see it. So yeah, if you see any wild animals, just kind of keep your voices down. You can take photos, but just pay attention to the photos. If there's an emergency, listen to tour guides. We'll make sure we get you where you need to. If somebody trips or falls or hurts themselves or not feeling well, let us know. We'll definitely make sure we get the proper medical attention to. Yes.
That information that will be available for the lecture as we go on the new plan.
The lecture we go on which plan?
Today when we're going, the information that will be together through the tour about the new plan.
The new planets. Planet 9, the one that where they the blue one. Yeah. We will. I'll give you as much information as I can. You stumped me right there already because I've been.
I was going to ask you what color blue. Is this correct?
Yes, it is. The blue planets, the new blue planets, the exoplanets that we're finding outside of our solar system. Tomorrow there's going to be a lecture, and there's a lecture that's online. It's a Von Karman lecture series that was particularly about exoplanets. Particularly on this one, we're going to be a lot more vague on it today. I am your information right now. I don't have anything like that.
That planet actually is in our solar system.
The new one?
Yes.
The one planet 9 that we're talking about? The one that's way out beyond?
Right.
Okay, that's the one you're talking about. Right. Okay, I was making sure. Was there a big announcement this morning is what I'm asking? Okay, no, you guys knew that. The way you said it was like the new one. Yeah, no, we've been searching about it. But right now we cannot.
Within the last 10 days, this is recent.
Yes. Well, I've been gone for the past 5, so I'm going to go cry in shame for a second. And then, so sit back, relax. We're going to watch a short video narrated by Han Solo himself. It does not include the blue planet, the new blue planet. Even if it is new, it's just with us. I'll be right back. So sit back, relax, enjoy this. Yay, space!
Answering these questions requires a journey to the planets and beyond. Our solar system coalesced out of a cosmic dust cloud some 4.5 billion years ago. Most of the dust condensed into the sun, which ignited into a nuclear furnace and burst into life as a star. The sun's internal fires provide the energy for almost every living process on Earth. Now we are exploring other places in our solar system where life might exist. Our search begins with Mercury, the planet closest to the sun.
4 billion years ago, the planet Mercury was struck by a 62-mile-wide asteroid, and it created a crater the size of Texas. That's just one example of the kind of violence that happened all the time when our solar system was forming. The next planet out from the sun is Venus, which has long been difficult for us to understand because of its very heavy atmosphere.
In the early 1990s, a JPL spacecraft used radar to penetrate the clouds of Venus. The result was a global three-dimensional map that revealed the surface of this hellish world, a place where even lead melts. No one expects to find life as we know it on Venus. Straight ahead is another planet. As this blue world comes into view, it is apparent that this is an entirely different kind of place. Our world enjoys an abundance of water, the great elixir of life. Making discoveries about our own planet from the vantage of space is one of JPL's proudest achievements.
For decades, JPL has been observing the mysteries of Earth from space. We study the atmosphere, looking at clouds and hurricanes. We assess changes in sea level and sea surface salinity, and look at phenomena such as El Niño and La Niña. We're developing instruments to assess small changes in Earth's topography to enable more accurate predictions of earthquakes and volcanoes.
JPL missions are also measuring the melting of ice sheets at the polar caps and atmospheric changes, including the vital ozone layer, so important to protecting life on Earth.
There are many Earth-observing missions on the horizon, and you'll soon be hearing much more about them. Some of these missions will measure sea level and wind patterns over the ocean. Another mission will measure the amount of carbon dioxide in the atmosphere. With more cases of drought occurring in the world, measuring soil moisture across the globe will be of key interest everywhere. Taken together, all of these missions are critical to better understanding the changes our planet is undergoing.
Carrying the spirit from Earth to planet Mars. Of all the other places in our solar system where life might exist, Mars may be the best bet. Yet the red planet is a world of extremes compared with our own. This is Olympus Mons, an ancient volcano as large as the state of Arizona. It rises 16 miles high. That's 3 times higher than Mount Everest. This gigantic scar is called Valles Marineris. Imagine the Grand Canyon stretching from coast to coast across North America, and you can begin to appreciate the scale of this massive trench. Though there are no signs of little green men here, primitive life forms could have once, or might still, exist on Mars.
That's one major reason why, since 1997, we have been operating spacecraft at Mars 24/7, 365 days a year. From orbit, Mars seems to be telling us that in the past it was a much warmer and wetter place. Wet enough that it possibly could have been water carving these channels that we see in the surface.
We know that wherever on Earth we find water, we find life. Might the same be true on Mars? That's why there's such an emphasis on finding Martian H2O.
We know there's water underneath the surface of Mars. Our spacecraft orbiting the planet have told us that. But to really understand the story and tale of that water, you have to get down there, move about, and explore. Sojourner was the first to do this back in 1997. But Sojourner was small, about the size of a microwave oven. Then came Spirit and Opportunity. They were about the size of a golf cart. But now there's Curiosity. It's the size of a car. It's so big that engineers at JPL had to invent a brand new way of getting to the surface. A way that some people, even engineers, thought was crazy. We weren't 100% sure it would work. It made for a very tense and dramatic landing that I will never forget.
Switch, things are looking good. About 100. His recording that we are seeing, G is on the order of 11 to 12 Earth keys. Commercial 2 is starting. Parachute is deployed. Teacher has separated where we found the ground. Standing by for batch cell separation. We are in powered flight. Standing by for sky crane. Sky crane is started. Touchdown confirmed. We're safe on Mars.
Got thumbnail.
Almost right away, Curiosity made a discovery that surprised and delighted scientists. A bed of rocks containing smooth pebbles. That means there's clear evidence that we were in what used to be a flowing stream on Mars. A few months later, the rover made an even more exciting discovery. The first sample ever, drilled from inside a rock on Mars, revealed an ancient wet environment with the right ingredients that could have sustained microorganisms. And who knows what other exciting discoveries await? As for the big question, is there life, or has there ever been life on Mars? Well, that's a question for future missions.
Mars is the last of the rocky planets as we journey further out into the solar system. Next, there's a gap where a planet might be expected to be. Instead, there's a vast swarm of rocks called the asteroid belt. A team of JPLers is constantly scanning the skies to track the potential threat of a wayward asteroid hitting our planet.
February 15th, 2013 was an extraordinary day for anyone interested in asteroids. On that day, a 130-foot asteroid passed within 17,200 miles of the Earth. That's the closest approach ever on record for an object of that size. Coincidentally, on that same day, a smaller asteroid did enter the atmosphere over Russia, exploded several miles in the sky, causing a brilliant fireball. It was the largest known asteroid to hit the Earth in over a century. This was a very vivid example of why it is so important to know more about these interesting objects. Meanwhile, out in the asteroid belt, a JPL spacecraft called Dawn is in the midst of its mission to explore two massive asteroids called Vesta and Ceres. They're sometimes referred to as protoplanets. What kept them from getting bigger was the influence of Jupiter.
The largest of all the planets in our solar system, Jupiter could hold 1,000 Earths. Like the Sun, it's a giant ball of mostly hydrogen gas with no solid surface. For 8 years, Jupiter had a visitor, a JPL spacecraft called Galileo. This orbiter explored not only Jupiter, but also the giant planet's 60-plus moons, each a fascinating world.
And now a new mission called Juno is on its way to Jupiter. Its purpose is to learn more about the origin of the planet. We don't really know everything about what lies beneath those beautiful swirling clouds. Is there a solid core? And if so, what size is it? Juno will tell us more not only about Jupiter, but should also yield clues about the origins of the entire solar system. Juno arrives at Jupiter in 2016. As it nears the planet, it'll be accelerating to a speed of 160,000 miles per hour. That will make it one of the fastest human-made objects in history.
Next comes the solar system's majestic gem, Saturn, the most serenely beautiful of all planets. Saturn's rings are made of ice and rock particles, some as small as dust, others as large as a house. In 2004, Saturn welcomed its first orbiting visitor, the JPL-built Cassini spacecraft. While Saturn and its rings have been bewitching to gaze upon, the biggest surprises have so far come from the Saturnian system of moons. Phoebe was the first moon Cassini trained its cameras upon. This was the best image we had of this moon before Cassini. This is Cassini's image. If you want to know what our planet was like when life first appeared, Titan may provide answers. Scientists believe that Titan's atmosphere resembles that of the primordial Earth. Cassini is now mapping Titan with its powerful radar. But it is Enceladus that has astonished scientists. This moon appears to have rolled over on its side. One result is that at the South Pole, where it should be the coldest, there seems to be an unknown heat source that is gushing up water like a Yellowstone geyser. Dubbed Cold Faithful, scientists were amazed to find evidence of water so far away from the sun. The number of places in the solar system suitable for life may be much larger than ever before imagined. Next, we catch sight of Uranus. While Earth is blue because of its water, this planet's color comes from an abundance of the gas methane. Uranus has had only one visitor, Voyager 2. After Uranus comes the planet Neptune, also visited by Voyager. Voyager 1 and 2 are now headed toward interstellar space. The vastness of space is almost unimaginable. The physical distances seem insurmountable. Even today, we have barely crossed the threshold into the larger universe that is all around us. But we can know about these distant places through telescopes. And from the vantage of space, we can behold glorious sights.
JPL's been a major contributor to a fleet of space telescopes. Using them and other techniques, astronomers have discovered almost 1,000 planets orbiting other stars now. Most of these planets are giant Jupiter-sized things, So the next big quest is to find an Earth-like planet orbiting another sun. By studying its chemical composition, we may be able to detect signs of life if it exists on a distant planet. If that happens, our understanding of our place in the universe will be profoundly changed.
The more we know, the more questions we have. And the ancient questions remain. What is out there? How did it all come to be? What will be our fate? But this much we can say. Every atom in your body was once inside a star. So the next time you look up into the night sky, remember, you are, quite literally, stardust. You and your dreams belong to the stars, and they to you.
Yay, space! The lights come on here in a sec. One person wanted to clap if you are. You watch 60 Minutes, don't you? 60 Minutes, that's what it is. So this weekend, 60 Minutes is a story on what Planet 9 is. Now, we've known about Planet 9 for a while. We've been working here, right? You're like, so there's still 3 ways to prove it. The thing about Planet 9 is the scientists that are working on it right there know it's there. And they have these beautiful mathematical equations about the knowledge of what's affecting everything around it, way beyond Pluto. Way beyond Pluto. That's why we call it Planet 9 right now, because it hasn't actually been fully discovered yet. We haven't seen it. Now, one of those scientists that are working on it, he's got a great analogy. He says, I can be walking down town and hear an ambulance 3 streets over and not need to see it until it's there. The data is there. There's a lot of influential things that are happening right there. People are about 95% sure, I'd even put it like 98% sure that Planet 9 is there, but we still do not have the full proof in order to say that it actually exists yet. Now, the reason we call it Planet 9, not Pluto. Pluto got knocked out. But this discovery that there's stuff out beyond Pluto is what knocked Pluto out. If Pluto is still a planet, we'd have to learn a few hundred other things and consider them planets today. Now, the 3 rules that make a planet are, number 1, you have to dominate your own orbit. Pluto doesn't have it. That's the one thing Pluto doesn't have. You have to be round, you have to orbit a star, and you have to dominate your own orbit. And that's what we do with Pluto, because Pluto is affected by Neptune. Now, what we think Planet 9 is, what their theories are right now with Planet 9 is it's doing a lot of stuff to the Kuiper Belt out there, way beyond right beyond Pluto, beyond the Pluto. And that's why, they think its orbit is quite some orbit. I think it's 114 years or something like that around the sun. That's how long it takes, which is why it's so hard to prove it right now. Because it's that far out there, it's so small, we actually don't have a telescope right now that we think can locate. We're working on that though, because we've got some other observatories out there. So that's a lot of the information I can give you right now on Planet 9, but we have this, and so it's not an exoplanet, it is a planet that we think is inside our solar system that hasn't fully been planted down yet. The guy who discovered it is the same guy who said we got to get rid of Pluto. And that guy gets hate mail sometimes and bad voicemails and things like that. But they also think there could possibly be Planet 10 out there, but he says Planet 10 is your generation, not our generation. So go find Planet 10. Some of the models around here. This is a half-scale model of Cassini. Now, Cassini has revolutionized the way that we look at Saturn, at the rings, at the moons around there. It's been up there for quite some time, but it will be ending its mission later this year. How do we end a spacecraft's mission? It's kind of like a Viking funeral. What we're going to do with these robots, we're actually going to send Cassini into Saturn. We're going to send it into its atmosphere, and we're going to vaporize it. That's say goodbye to it. We don't want it to crash into those moons around Saturn that may or may not have water, which may or may not have life. It's a whole department here called planetary detection. So that's how we're going to end Cassini's mission. But they've taken some beautiful photos of the rings and the moons. And a lot of people like to ask me, what's that gold shiny stuff on here? Well, that's called thermal blanketing. That is there to protect the spacecraft. If you're going close to the sun, you're going to be silver or gold to reflect those rays back at the sun. Like you're protecting your car from overheating, you put that right in the windshield, reflects those rays back at the sun. If you're going far away from the sun, like Voyager 1 and Voyager 2 over there, in the nice dark, and absorb as much of that as you possibly can, retain some of that heat. This is also, it's made out of a cacti, which is it's like mylar, it's like Kevlar for the spacecraft. There's micrometeorites and little pebbles and little small things floating around there. They're still traveling 20,000 miles an hour relative to the spacecraft. Could tear a nice big hole in it, so we want to protect it from all of those. Now, can anybody tell me what planet we are observing the most? I'll get your question in a second. What planet are we looking at the most? Earth. Close. Closer to the sun than that. Earth. That's right. This is the planet we're observing the most. We have one Earth per billions of miles. We want to make sure that we take care of it. We have the most missions here on Earth we're observing right now. This is called soil moisture active passive, or SNAP. We love acronyms here at APL. Now, this is observing how much moisture is left in the soil. You can predict drought, you can predict flooding, all those great things. But as I'm saying, it is NASA's job. What we do is we gather all this data, give it to us, the people, and also to the politicians. It's up to us to do something with that. Back here, we have a one-scale model of Juno. Juno, the spacecraft, is the farthest traveling solar-powered spacecraft we've ever launched. This is roughly the size of a basketball court. So, say this was in your backyard. You could run your house and your neighbor's house on both sides with those solar panels. Fortunately, at Jupiter, we're lucky if we can run a toaster on them. That's how efficient the spacecraft has to be, because Jupiter gets roughly 4% of the sunlight that we get here on Earth. So it has to be so big. Of course, you can't launch a basketball court from Kennedy Space Center. So they call it spacecraft origami, where it's all folded up and it expands and does the line you see out there. That's the spacecraft that you see right here. Now, is anybody familiar with the Juno orbiter insertion that happened on the 4th of July this year? Anybody pay attention to that? Some of you are nodding your heads, some of you are like, I don't know what that is. We have spacecraft, actually, this one, inserted into Jupiter's orbit this year. We're doing polar orbits of Jupiter. Jupiter is the biggest and the fattest of the planets, giving off more radiation than receives from the sun. It's going to do a number on the spacecraft, which is why we use solar panels rather than, lovely segue right there, RTGs, radioisotope thermoelectric generator. Don't have to remember those words. Just remember RTG and you're solid. It's like a nuclear battery. So you got plutonium-238 in there. If you're going to Google it, make sure you Google plutonium-238. Otherwise, you'll end up on a government watch list. And that is red hot. And as that heat, as it decays, that heat is what comes off. You have a thermocoupler on there, and that turns that heat into electricity. That's what powers our. So a lot of times, if you're going to beyond the asteroid belt, you're going to use an RTG. This one, Voyager 1 and Voyager 2, has three RTGs, and that's why we're still being able to communicate with it a little bit today. 39 years ago it launched, and this is my personal favorite spacecraft, because right here on the front. Gold shiny thing is the gold record with the sounds of Earth. Who's familiar with Carl Sagan? Cool. Who's familiar with the gold record? Oh, a few people. So Sounds of Earth, we have greetings in over 55 different languages on here. We have sounds from babbling brooks to tribes to all sorts of wonderful things. We have images that are embedded and coded on it, but we also have music on here. And we have Stravinsky, we have Bach, we have Beethoven, and then we got Chuck Berry, we got Louis Armstrong, and my personal favorite is Blind Willie Johnson. Anybody familiar with Blind Willie Johnson? A couple people. I like seeing that. I like when. That's amazing, because when he died in obscurity. He died penniless. And it wasn't a nickname, the man was blind. But his song, Dark Was the Night, Cold as the Ground, has reached interstellar space. And I think that's pretty cool. What was your question, sir?
Two questions.
Number one.
First, is there a quiz at the end of the store?
There is a quiz at the end of the store? No.
The second real question is, what's causing the end of Cassini? Is it running out of propellant?
So that uses an RTG, and I think Cassini is out of hydrogen propellant right now. So the reason you would do that to an end of the mission, same thing's going to happen with Juno, is you don't want to be able to lose control. So even not having power, not having any propellant like that, we can't maneuver it. So if something were to happen and crash into one of those moons that have water, it's over. So rather than accidentally do that, we're going to get as much information as we can as we go in. We're just going to have a couple instruments still on, and that'll be it. So usually it's a time thing, also with decaying orbit. So the longer you can Saturn, we've been able to do wonderful things, but at this point we can't propel it anymore, and we put it in its final stage of slowly down.
Yeah. Harrison Ford was mentioning something about we come from stars
Yeah, that Harrison.
Is that any truth to that?
That in truth is that we are quite literally stardust. You and the stars belong to the thing it says at the end. We are all made of the same elements that you find in the stars. Everything that has come, all elements that we know of, are all the same that are found in the stars. That is what he's trying to imply.
But some of those are only made in stars.
Yes. So I feel like we're quickly approaching the line between science and religion. And I want to point out that the two are not mutually exclusive. We have a lot of very religious people who work here. They are not mutually exclusive. The idea that these elements are created by stars, that they have come from stars, that they have come from different places around the world, does not necessarily mean we know where that came from. So, I want to point that out right there. Science and religion can get along. And we hope you guys do. So if you have any further follow-up questions on that, I'd be more than happy to talk about that. Anything else? Here's what we're going to do. We're going to let you wander around for about a minute or 3 or 4, maybe use the restroom. Now is a good time. Through those curtains to the left. The other thing I will say, we're going to split you up from here into 3 different groups. There's a museum next door that we will go to part of the tour, so I ask you stay in this area right now, and when your group gets to go there, you'll be able to, rather than trying to round everybody up. So have fun, wander around. If you have any questions, just stand in the back.
Uzun bir girişten sonra nihayet başlayabildik. Bu Cassini uzay aracının ikizi burada. Satürn'ü gözetliyor. Gelecek yıl Satürn'e düşürülecek. Türkiye'de açılması için 20 defa teklif edilmiş. Hepsinde de reddedilmiş.
You're just hanging out here, Brett. Oh, okay. Take a look at the models and all that. You're going to go where?
Yeah, we're going to go straight up to you.
Mars'a giden aracın sorry.
By the time you hear it 500 times, you get all these different pieces, you put it together and you figure out what he's telling you. But as you can imagine, as we get further, we get less and less pieces. And at some point, there's going to be something missing and you can't figure out what's trying to tell us.
If you're part of the Visitor Day Tour, well, you can line up on the opposite side of the auditorium, please. Visitor Day Tour on the other side.
Visitor Day over there by Snap and Cassini, Everyday Spacer, Juno, and
Delphi over here.
Delphi over here.
I like your glasses, they're beautiful. Or they're handsome. Right.
All right, folks, if I could ask our Delphi group to go ahead and follow this up, please.
If you are with Delphi, you're exiting out now.
And it was Jake Gill. Yep, thanks for that. I'll keep it. Ready to go? So if you guys would like to follow Mark in the red. Good work, folks. Here with Everyday Spacer. Hang on, Mark.
Come on in, gather around the rovers here for just a few moments. Right? Thanks for coming. What? Thanks for coming. You guys eat everything? If you'd like to go over to Laboratuarı, I think you're ready. Is this everybody? No, this can't be everybody. Brian, check your math. I don't think I have everybody. Oh, maybe it is. I'm at 16. Curtis, just make sure that, not you, Curtis. Brian, you copy? Yeah, go ahead. I might be missing a couple, maybe. Just double check with your group. So how you guys doing, by the way? Everybody good?
Great.
Good. Right. So my name is Mark. I'll be probably your talking tour guide today. There'll be somebody else bringing up tail end, but she's, I don't believe, one of our talkers, as it were. But anyway, thanks for coming out to visit us, you guys. Glad y'all made it today. So, and obviously, I'd much rather make this a conversation. So if you guys have questions, we're such a small group. Don't hesitate to just yell at me. This can be a whole lot less formal because we're such a small group. Let me just grab this real quick. Yeah, go ahead. Yeah, for sure. We'll do. Okay, so anyway, welcome to our museum. First of all, we'll start here. And I just want to talk about these models. I'll explain how the museum is set up, and then we'll give you guys a little time to kind of wander around and take a look at the place. But the reason we stop here generally is because these two models are actual size, first of all, and and they do represent the first two generations of rovers that we ever sent to Mars. So you guys might know we're kind of famous for our rovers around here. The first time a rover ever landed on Mars was that teeny tiny little one you see on the far side there. Her name was Sojourner. She was part of a mission called the Mars Pathfinder mission. Now that landed on Mars on 4th of July of 1997. First rover, like I said, ever on Mars. It really wasn't so much an engineering mission, or rather, it wasn't so much a science mission as it was an engineering mission. So what we were really trying to do with that spacecraft, the whole mission really, was to figure out if the way we were trying to land was actually going to work. So have you folks ever seen video of how we bounced onto Mars back in the day? So if you have not, this screen behind me will play it momentarily. It's on like a few minute loop. If you happen to see it while I'm blabbing at you, get my attention. I can talk you through it. But the idea was what we used to do, and the reason we did it, by the way, was to kind of take some of the unknowns out of the equation. The Martian atmosphere varies in density quite a bit, and it can really change how the spacecraft are landing on the surface. And the problem is it puffs up, it shrinks depending on how badly the wind is blowing on the surface, and we have no real-time control over the spacecraft because Mars is so far away that a radio signal, on average, even at the speed of light, remember that's how fast radio signals travel, takes an average of about 14 minutes to travel between the planets one way. So, you know, by the time you get a signal that something's going wrong with the spacecraft, there's pretty much nothing you can do. So the airbags were sort of a solution to help solve that problem, and they were huge. They were basically, you know, once they were inflated, they were about the size of the ceiling in here and would have filled up most of the space we're in. And the idea was we kind of origami these rovers into this little lander, we called it, with these airbags on the outside that were flattened, much like a car airbag. And then as we plowed through the Martian atmosphere, they you know, inflated. We got to about somewhere between 20 and 50 meters off the ground, cut the airbags, and then it bounced the rest of the way. So it worked out okay. Maybe not the most ideal way to land, but that's all that mission's job was, to figure out if that was if that would work successfully. So it did. We were like super happy. The rover was only supposed to last a week. It lasted almost 3 months, which was pretty crazy. We were really thrilled about that. But then the question was, okay, well, how big of a rover can we build and what can we accomplish and still use that landing technology since we know it works? So that evolved into twins of this thing. So they were called Spirit and Opportunity. They landed on Mars in January of 2004. Here we go. So this is how it went. So it starts very similarly to what you saw. But this is where things begin to change. So when the heat shield comes off, instead of having the rover wearing this rocket pack, we've got this balloon system basically descending on this bridle, we call it. And there's a radar system, really primitive radar system, that's looking at the surface. That's about real time, by the way. It's about a tenth of a second. Boom, these whole things inflate. And then at a certain height off the ground, we cut the air, fill them up, cut the balloons, and bounce. And what's crazy about this system is the problem with it is that you have to pick an area that you hope is relatively free of large boulders, which often equates to scientifically boring. So there was quite a hot debate between the two rovers and the science teams and the engineering teams. But look at this spacecraft origami, we call this. And this is on our website. You can go back and see this again. But the problem with it was there were so many moving parts, too. Any one motor that fails, there were so many little single-point failures that things could have gone terribly wrong. Like, all these parts are physically, like, wired together. And we have these little devices that are called pyros. And they're basically like explosive wire cutters. Like a little guillotine is what they sort of look like. And they have to fire to slice the wires to release parts. So like all these panels are all physically tied together at the top, so that when we're bouncing, we're not rattling all over the place. Yeah?
Because this is still so abstract to me.
Yeah.
Now, I'm seeing, the men and the women seated there,
Yeah.
watching things.
Yeah.
Is it that there's just, is everyone involved in the opening, like you do this and
Some
then I do
component
that?
usually, yeah, exactly
So
right.
it's a whole group effort to unfold.
Yeah, and it's the whole process of landing, really.
The
Once we
landing.
land on the ground, this usually happens a little later. So like for in this example, this video, once we hit the ground and finished, The only thing that had to happen immediately were the thing had to unfold and we had to get the solar panels open. Everything after that took days. So like entirely, it was 12 days before we got Curiosity, or got Spirit off the lander. So that's the landing portion there. We call that the lander. It took us 12 days to get it off of there, unfolded and completely deployed, because they made sure every little thing worked. But that whole landing system, as you're plowing through the atmosphere, there are different teams responsible for different parts of that. So you may have, it's hard to see in the video you guys watched, but the same was the case for Curiosity, where there was a team responsible for like the heat shield coming on. And when that happened and we got the radio signals to confirm that, you saw those guys all, yeah, you know, high-fiving. So like, okay, it's not on us, you know, something goes wrong. And then the parachute team, kind of the same thing happens. When the parachute deploys and we get the signal that that's okay, then they flipped out. So it's kind of throughout the room, you'd see these little teams kind of going, yeah, cool, yeah, cool. So there was, yeah, there's a lot of that. So they certainly have, once you, especially when you get to that room, you've got, you know, the people kind of really specifically for that purpose, you know, make sure that that
balloon-like objects with them, so they're just wrapped.
So they just stay there. Yeah. So that didn't show much. Show it. This is another one. This is a real picture. So once the airbags deflate, they actually had a system internally that was almost like a fishing rod system, where we had these little cables connected inside and a little spool built into that. So the idea was by just pulling the airbags down the drum. Concerns that are why they don't turns out that area was scientifically just dead. There was nothing going on there. It took us forever to find evidence of water. But 3 weeks later, Opportunity Land, we bounced into this tiny little crater that was maybe 15, 20 meters across. And right smack in front of our faces when this thing unfolded was exposed right up. So the scientists went completely crazy. They lost it. So because that was evidence of water right there in front of our faces. That's what so they spent a whole bit of time here, as you can see, driving around, poking around, and this is a mosaic of images you took photos before we left. You know, sitting parallel to our landing site. Now these twins were only supposed to last 3 months. That was the mission for deployment. The teams were guardedly optimistic that if we could survive that crazy landing, that we could perhaps eke out something on the order of a year. As it turns out, Spirit, the first one, lasted a little over 6 years, which was pretty amazing. But it's nuttier because the second one, Opportunity, is still working. Remember, that was January 2004, so it's still working all these years later. So there's kind of a, kind of a competition now between Curiosity and Opportunity. Because that's a long time to ask a rover to live. And now the Curiosity team, the new rover you saw in the video, they're telling us already they're not going to be happy unless they make at least 10 years. So, kind of a contest going on there. But we'll see how that plays out. But these 2 rovers went to Mars. Scientifically, their goal was to look for evidence of water. And they did that by looking at the minerals. So there are certain minerals that can't exist unless water was there to help that mineral form. One of the examples we use here on Earth all the time is hematite. They make a lot of jewelry out of it. Sometimes it appears as like a black rock with lots of little silvery speckles in it. So they polish that up and make jewelry out of it and stuff. So it's very common, but it needs water to form. So that's the kind of stuff we were looking for on Mars. And it turns out we found a lot of it right in here, in a different presentation, but a lot of the same stuff. And then as we continue to drive around, some of these pictures, I'll show it on some of these slideshows throughout the room. But we turned out stuff that was like almost pure, like silica beach sand, right? Amazing stuff. And then in one instance, we turned up this stuff that was like opal. And that stuff is generally very indicative of really briny, salty oceans having been there in the past. So anyway, found evidence of water all over the place with these two rovers, continue to find it with Opportunity, verifying it again with Curiosity, the new one, finding evidence where it lives. And basically that's what led to Curiosity. I'll mention this again later when we see that model, but basically the new rover, her job is a chemist, where we're looking for evidence of the actual ingredients that make up life, so she can actually find those ingredients, and has in fact found them all, which is pretty crazy. And then, yeah, so that's basically what we were trying to do. We went up there with the chemistry suite to help look for those ingredients. So found all those ingredients, and that will lead to what's called the 2020 rover. We don't actually have a name for it yet. Right now it says Mars 2020. And I'll talk more about that later when we get to where we build our spacecraft. But that will take, further the science even more, once we get up there. So anyway, that's kind of the short story of the rovers. Maybe not so short, but let me explain our museum and I'll let you guys take a look around. It all starts with that image of the sun, and it goes clockwise in the order of the planets. You certainly do not need to visit it in that order, but that's how we presented it. And you'll notice as each planet goes around the room, there's at least one of these information panels for each planet. Earth has a few as it wraps around the corner here. But here's the deal. This picture of the sun is actually this size on purpose. Because one of the things we wanted to try and do in the museum was give folks an idea for scale, how big things were compared to each other. So at each planet, you're going to see something like this. And they vary in size pretty greatly. But like in this instance, this is supposed to show you, obviously not what Mercury looks like. These are pictures. But this is supposed to show you how big Mercury would be if that were the size of the sun. So we didn't have enough room or money to build a giant 3D ball of the sun. But, use your imagination, remember, and, as you do that. You'll see Earth over there, just on the other side of, on this side of the globe, about the size of a golf ball. You'll see Jupiter when you get around the bend, around the corner. She's about the size of a beach ball, largest planet. Remember, you can get over 1,000 of those inside the sun. So this may not even do it justice. It's just so big. And the other thing I wanted to explain before you go, around the room, the other marbles, all the outer planets, Jupiter, Saturn, Uranus, and Neptune, they all have rings, actually. We didn't necessarily know that until we got there, but they all have rings. Nothing like Saturn's rings, of course. But we did put those rings on these marbles, not so much to show you how much ring is there. In fact, if you were look straight back from where I'm standing, you can see Uranus and Neptune. Right, you guys see that back there, the marbles for those two? They're about the size of a grapefruit. The reason we put the rings on them, because like I said, I don't think it does a good job of representing how much ring is really there, but more to show you the axis of the planet. Because look at Uranus. She's tilted completely on her side. And if we didn't put those rings on it, you wouldn't know that. Right? It'd be like another big white marble. So, as you go around the room, notice that. And we have an actual size model of Galileo. That's what this gold thing, this gold point that leads towards the back of the room. That's the largest spacecraft model we still have. It's the second largest spacecraft we built. But it spent nearly 8 years orbiting Jupiter. So it got there in December of '95, and its mission ended, I want to say it was in September of 2003, when we kind of swan dove it into Jupiter itself to kind of vaporize the spacecraft, get rid of it. And then, what else is around? So we've got an infrared camera over there in the back right behind this little blue piece of wall, which is pretty cool. Some meteorite samples, a sample of one of the world's lightest solids, this stuff called aerogel. And on the back side of this picture, there's a display screen, and I'll play for you guys a video. It's called 7 Minutes of Terror. It's a little more data, a little more information about how we landed Curiosity on Mars. Don't feel like you have to watch it. It is on our YouTube channel and stuff, but if you want to see it, I'll play it for you. Oh, and don't miss our moon rock. So in that little pyramid there, this is the moon rock that came back on Apollo 16 back in 1972. That's what this is in here. So yeah, kind of cool. Figure that rock is pushing about 4 billion years old. And we have found rocks on Earth that old, but they're really rare. So yeah, so that's pretty cool. Not that the moon rocks are rare, right?
Base material for these panels, is that graphite?
No, it's aluminum. Aluminum honeycomb. Yeah. So those are aluminum. Exactly. In space, or it's fine. It's actually, they're not too hard to find if you look in the right places. Like they actually use asteroid hunters, guys who got some luck, this is a hobby. Yeah. And what they do is they'll use places that are like permanently frozen, like Iceland and places like that. And you put them on the rock frozen together, and there's a black rock out there. And they figure like more often than not, they're going to be an asteroid. So they'll get a check out to make sure, but either they stand out and they get this area that doesn't get a lot of coverage or change weather, they're fairly easy to spot, places like that. But they're still pretty expensive. If you look for them. There's like rock shops and stuff.
Right, okay.
They're still not cheap.
So like golf ball size asteroid.
Yeah, I don't know what that would cost, but
you have an idea. Okay.
Yeah, I really
I just wondered.
And then we have 3 of them here. Which the 3 we have on as samples in our little display, they're pretty cool actually.
Are they heavy?
These are pretty heavy, yeah. But they think that they thought at first that these 3 came from the same asteroid called Vesta, which is one of the bigger asteroids in the asteroid belt. It's the second one. And then we had a spacecraft called Dawn actually go visit that asteroid, and based on what we saw there, we were like, yeah, those definitely came from that asteroid. Definitely chunks from the same thing. The chemistry was almost all the same.
So where you would find this would be in the snow.
They often find them in the snow, yeah. Places where it's freshly snowed, or where there's like, glaciers where the ice doesn't change a lot.
See, I never knew that.
Yeah, that's what those rock hunters that try to make money doing this, that's where they'll
collect
go.
rocks, but
Yeah.
it's more of taking a piece of
Yeah, like where you
country
were,
home.
right, yeah. That's what it always is. Right, I have rock hunters all over from when I was in Scouts. Right. So I'll play that video for you guys. Like I said, don't feel like you have to watch it, but I'll give it a ring. It's on the screen here.
Personality for this.
Oh, thanks. It's fun. I love it.
Oh, yeah. Now, do you rotate, or this is?
We do, yeah. So this is kind of our main gig.
When people look at it, it looks crazy. It's a very natural thing. Sometimes when we look at it, it is the result of reason, engineering, thought. And it still looks great. The top of the atmosphere, down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away. So when we first get word that we've touched the top of the atmosphere, the vehicle has been live, dead, on the surface for at least 7 minutes.
Entry, descent, landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0, in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself, with no help program. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we have never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical diversion. We fly off to the sun.
Diverting away from the parachute killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land, and we're head straight down to the bottom of the crater, right beside a 6-kilometer high mountain.
You can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud would then go and land on the rover. It could damage mechanisms, and it could damage instruments. So the way we solved that problem was by using the Skyscraper.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit on its wings on the surface.
As the rover touches down and is now on the ground, in the same stage, it's in a collision course with the rover. You must cut the bridle immediately and fly to the same stage to a safe distance from the rover.
Yeah. Is that like a sponge type? On the real spacecraft, it's almost like a gel. A gel. So that's how that model maker was able to do it for this. But yeah, it's almost like a jelly looking stuff. It's kind of shiny actually. And the idea was really just to keep rocks out of the spokes. Oh, okay. Because the spokes sort of act, even though we're not going really quick, like a shock a little bit. That's the idea, yeah. Because we don't have any other suspension systems. So the reels are a little compressible. So it was debatable whether or not it was necessary, but they decided to do it anyway.
I'm surprised they didn't put any kind of a
cap over it?
well, no, a shock system on it.
Well, the thing is, there's a lot less gravity on Mars. So it's like 38% of Earth.
Yeah.
So,
Aydan getirilen taş.
Yeah, and so that was, they were debating that, whether or not they really, I remember hearing somebody saying, I don't know, that's not right. And then on the real rover, we actually have little hubcaps that say NASA, the NASA logo on each wheel. And it was funny, one of the first tours I did, well, I wouldn't say one of the first tours, but not long after the twins landed on Mars, I was taken around this small group, and I knew they were from some company that was a contractor that we used on the rover. Turns out that's the only thing they did. They created those little NASA logo caps because they were like, oh yeah, they were crazy because they had to last in the temperatures because the temperatures change more than 150 degrees between day and night. So they had to do a stay on. It was crazy. Yeah, they were cool. All right, guys, we got to get going to the next stop. The other group's on our heels.
The actual testing that they did the first time, did they do it somewhere around here? Or
For the rover itself, or
yeah,
because we were never able to fully bounce.
Oh, you never? Okay.
We did it in a vacuum chamber from about 60 feet.
Okay. Okay.
So yeah, they kind of simulated it as much as they could.
Rocks like this.
We're going.
Oh, we got that.
Good. I know, some blue sky. How about that? It'll last for a while, right?
Yeah.
I think we're going to see any tomorrow.
How big's the campus?
About 177 acres, about twice the size of Disneyland.
Burada beklerken karşı taraftaki dağları göstereyim. Bu dağın ismi Mount Wilson. Tepesinde de Mount Wilson gözlemevi var. Hubble'ın evrenin genişlediğini bulduğu gözlemevi. Buradan görünüyor ama şu an bulutlar var üstünde. What?
L-band is one of them.
Konya'dan Ali Saraç Hoca buradan selam göndermemizi istemiş. Şu an izliyormuş. Selam gönderiyoruz ona. Seçkin diye de bir arkadaş var. 4-5 seferdir mesaj gönderiyor. Tuğba diye bir sevgilisi varmış. Ona NASA'dan onun sevdiğini söylememi istiyor. Bak Tuğba, akıllı ol.
Are you recording my call?
Kind of.
I don't want you to do that. That's okay. Alright guys, we're going to keep this short because I'm already way late. But I wanted you all to see this really quickly. This is an actual size model of Curiosity. So now that you've seen the other two rover models, you get an idea for how big this thing really was. We went from about 30 pounds with Sojourner to about 385 with Spirit and Opportunity to just a few pounds shy of a ton with this thing. So it's actually the heaviest thing ever landed on Mars. And also, you may notice not solar powered. You may have noticed the solar, the solar panels on the models. This time around, we're nuclear powered. Now, I think they talked about the RTGs, right? The radioisotope systems on the other spacecraft. We're using one of those this time around. It's that white object, fins on the tail end. The reason we used that this time was a couple of reasons. We wanted to give the scientists a little more leeway in where they could go. If you're going to use the solar power, or if you're going to use solar power on a Mars mission, ideally you want to stay somewhere near the equator. So we wanted to give the scientists more range north and south to pick a landing spot. So that was one of the reasons we did it. And then also because we had to guarantee a much longer mission. So previously, like I mentioned downstairs, the little one only had to last a week. These are the mission requirements from NASA. Only had to last a week. Spirit and Opportunity, 90 days was the mission. Here, we had to guarantee a full Martian year, which is almost 2 Earth years. It's like 687 Earth days. So, and the reason that's a challenge when you're dealing with a solar panel spacecraft as opposed to this, there's a lot of dust that flows around in the atmosphere on Mars. Our go-to example is that back in 2001, the entire planet of Mars was covered by a dust storm that lasted about 9 months. If you had a solar-powered spacecraft on the surface there, that would have been the end of it. It would have never been made. So this time around, we figured, all right, this is the only way we can guarantee that mission. NASA totally understood it. It wasn't like they had to argue that point, but that's kind of why we did it this time. So it does open up a lot of other avenues for us. We don't drive around at night, which we don't have, so we can't do that. But it does allow us to operate basically year-round. We don't have to worry about the weather. We don't have to worry about dust storms. We don't have to worry about winter, because a lot of times our solar-powered rovers hibernate during winter. So there's 4 months out of the year where we don't do a whole lot. We may sit parked on a hillside for 4 months at a time. We've done that in the past. So in fact, this past Martian winter was the first time we ever operated one of the rovers, which was Opportunity, during the Martian winter, solar-powered spacecraft. So it's risky because, the problem is there's not enough daylight to charge your batteries. So, and the problem is you need the batteries to be full before the sun goes down because you need the energy in the batteries to run heaters to keep the spacecraft nice and comfortable. So, you're generally quite limited in what you can do during Martian winter, but that wasn't the case with this. So we can kind of go as much as we like. It's entirely aluminum, well, not entirely. The tubing, the legs, and the spokes and the wheels on the real spacecraft are titanium, but everything else is aluminum. Okay?
Any suspension at all on this one?
None. Just the flexibility within the wheels. That's, so the wheels they're crushable to some extent. Yeah. Okay. That's it. Yeah. And the suspension system we see on all these rover models, it's called the rocker bogey suspension system. Basically, we like it for a couple reasons. One, because it only connects to the rover in one place, so that limits where dust and stuff can get in. So we like that. And then it also allows us to basically kind of caterpillar over rocks. So we can climb rocks that are close to 1.5 times the wheel diameter and still keep the rover level. Nice. And then then this time around, because it's so much larger, we actually have this transmission that runs across the deck. So as one side's climbing, we're effectively pressing the other side. So we're trying to keep all 6 wheels in contact, giving us traction as we climb around. Okay.
I understand that the Martian service is punching holes in the wheels.
Punching holes, yeah. Some of the wheels are really, really thin, as you can imagine, because we didn't have a lot of weight to play with. So some of them were actually perforated by the rocks up there. In the past, with the previous rovers, we would drive over rocks, and a lot of times they would just kind of push, back into the sand. This time the rocks are anchored quite well, so they're pushing back. And what they've learned is, as we approach a rock, let's say, as that front wheel is trying to gain traction to climb up the rock, the other 2 are pushing, because it's 6-wheel drive. There's electric motors in each hub, in each wheel hub. So, we were effectively causing the damage somewhat ourselves. So once they kind of realized that was going on, we started doing a couple things. We drive the rover backwards now on occasion, which is good. And then they've also programmed it a little bit so that when that first wheel, if they start detecting some drag there, then it speeds up the rotation. So they can hopefully climb a little more quickly, while the other ones are sort of helping it up and over rather than trying to just ram it into the rock. So we'll see how that plays out. But for the next rover, the Mars 2020, we'll talk about later, they're already redesigning the wheels. We can't make them any heavier. We don't have any mass really to play with. So they're going to be narrower and so they can make them thicker. That's usually the plan. And then the last thing I'll mention is the holes in the wheels. They're there for a couple different reasons, and I have to mention it. One was to let dirt out of the wheel. That was kind of the obvious reason. They could collect a lot of dirt, so we wanted some way to get the dirt out. Another way was to allow us to utilize a technique they call visual odometry, which is where if we're driving around on Mars, we look at the surface where the patterns are different, so we can stamp this pattern into the dirt. And then you can compare that against what you told the rover to do. You know the circumference of the ring behind those spots. Get a rough estimate for how far you drove. So there's 2 of the reasons. The third reason is actually the kind of fun reason. Our original tread design actually had the letters JPL on the wheel every now and then. NASA headquarters was like, no. You guys can't do that. We're paying for this. So the engineers, being a little upset but clever, decided, hey, I wonder if anybody would remember what Morse code looks like. So there's a 3 lines with a dot and dash pattern. Yeah, you can guess what the letters are. Yeah, right, we're going to do it once again. All right, guys, we got to go to the next stop.
Curiosity'nin tekerine JPL yazmak istemişler. Ama NASA bunun parasını biz ödüyoruz, sana vermeyiz demişler. O da mühendisler de Morse koduyla JPL yazmışlar. Şu an uzay araçlarının kontrol merkezine giriyoruz. Evet, şu an uzay aracının kumanda merkezindeyiz.
So you guys can stay at the window if you like, or you can grab a seat. Since we're a small group, I'll let you kind of do whatever. But I will talk now so that I can stay on time before the other group gets up here. But welcome to our mission control. This is what you saw in the video when everybody went nuts when we landed on Mars. But I will say, as much as the room directly in front of you was full of people going crazy, most of what they showed you in the video was downstairs on the left, in that room that is empty behind the glass there. You see that over there on the left? So that's what's called the mission support area. And the thing is, you guys know, because we deal with robots, it's a little bit different. You know, it's not like the human mission control in Houston, Texas. That room has, what, a dozen people or so in it 24 hours a day, because they're worried about the astronauts on the space station. We've got 6 folks on the International Space Station right now. You've got to worry about their health and welfare, of course, but you've also got to worry about the space station. There's 50 million systems on that thing, you know, keeping it running. And as much as the astronauts are great at what they do, they don't have time to monitor all that stuff. They're conducting experiments. Yes. Certainly they can do some maintenance, but they just can't run the whole thing. They just can't do it. So the crew in Houston is remotely monitoring all the systems on the station 24/7. So there's always a bunch of people down there. For us, because our spacecraft are robots, it's a little different. These guys and gals say it's a lot like flying an airplane. It's exciting twice, which would be takeoff and landing, as you would presume, right? So takeoff, launching the rocket, or arriving at our destination. So on any other day, there's not a lot of people in here. The way it works on a normal day is all of our missions have a job called an ACE. And you can actually see some of the ACE workstations right down in front of you guys. And there's a bunch of them that actually sit in a different building that aren't in here. But here's the way the ACE fits into the puzzle. So imagine, let's use the rover for example. Imagine the rover sitting there on Mars. You folks know there's like a whole group of scientists kind of behind the scenes, right? And their job is to figure out what they want the robot to do. Like, what rock are we going to go kick around on Mars tomorrow, right? All right. So once they kind of determine their science goals, then that information is given to the engineering team. And then the engineers actually write the program, the sequence we call it, that will tell the rover how to do those things. So how to get to where it needs to go and all this. Once that sequence is ready to go, it's given to the ACE. And then the ACE basically works with these folks downstairs, and what those folks do, right smack in front of us in those first few rows, those folks run what is called the NASA Deep Space Network. It's the communications infrastructure we use to communicate with all these deep space missions. So it's a NASA thing, JPL runs it for them. And what it basically consists of are these antennas that you see in the images downstairs, these big dish-shaped antennas that are spaced around the world equidistantly. You guys might know the problem with a dish antenna, as good as they are at sending signals very far away, long distances, they can only send signals in the direction they're pointed. And that's sort of the challenge. So, if we're trying to send instructions to a rover sitting on Mars, we need to have an antenna pointed at Mars. Okay, that's not a big deal, we can do that. But the problem is these antennas are stuck on Earth, which is busy rotating all day. So it becomes somewhat challenging. So the Deep Space Network was set up, basically, you can see the names of the cities on the chart downstairs. You see Madrid, Spain. Goldstone's actually right here in California, right above Barstow. So it's actually on Fort Irwin's property. You guys ever driven to Vegas from here? There's the Fort Irwin exit right there. There's a huge military training camp out there. We're actually on the property there. You can visit it. You just need to set the tours up in advance. And then right outside of Canberra, Australia. And the reason those three cities is, one, they're all politically stable, which is a big deal, but also because they're roughly 120 degrees apart. So the idea was whack the Earth into thirds so that no matter where you are in space, you can see one of our antenna stations. So it gives us the ability to contact you pretty much any time we need to. So the chart you see downstairs, kind of left of center, that shows you a few different things. So first of all, it shows you all the antennas we have by location. So, and then the ones that are active at the moment have the squiggly lines. Can you guys all see those, right? Pretty obvious, right? The squiggly lines are the radio signals, supposed to represent the radio signals. If they're going up, that usually means we're sending instructions. If they're coming down, we're downloading. Every antenna, by the way, has a 2-digit number at the bottom. That's quite literally just the number of the antenna. So you guys all see that there. And then at the top of each one, well, the ones that are communicating in particular, you'll see kind of a letter code, right? That's the abbreviation for the name of the spacecraft. So what happens with this thing, and this wasn't working this morning, so let me see if it's working right now. Let's see. No, it's not. Okay. So I don't have control over it, but basically it would show you the same thing. What it does downstairs is it highlights an antenna, turns it green. All that does is change the other two displays. So like right now you see the antenna number 43, right? How it's green on the left side, right? So what it does in the center screen, it draws an animated but accurate picture of the antenna. So we have this model of the antenna here. That puts that model in exactly the position the antenna is in right at this moment. So here we go, Canberra 34. What's also cool, though, is right next to that, it draws an image of the spacecraft. Again, animated, but again, accurate. So that shows you where that is right now. So what's kind of cool about that whole thing is that's a demo you guys can play with on our website. So you get to keep your badges. Our website's listed on the back in crazy tiny letters on the bottom, but it's there. But this particular demo is called Eyes, like your eyes, on the solar system. Eyes on the solar system. And it's a real-time spacecraft simulator. The version you have at home is really cool because you've got full, like, click and drag control of your perspective. So, like, right here, this kind of always defaults to a camera orbiting the spacecraft, right? So that's what you're seeing there. But you can click on it, drag it around, see whatever you want to see. The star field in the background is actually correctly represented. See, look at that little cluster going by in the top left there. What you'll also notice
is that off in the distance you're going to see other text on occasion. Those are the other spacecraft or bodies in the solar system. When you're playing with this at home, just roll your mouse over the text, click it, and it will fly you to whatever that object is. So you can quite literally hop around the solar system all day and see what our spacecraft are doing. Really, really cool. They've won all kinds of awards with this particular demo. So the antennas themselves, there's two different sizes in the network. It's easier to see by looking at that chart of all the antennas. But you notice the first antenna by location is larger than the rest? You guys notice that? So what, 63, 14, and 43 are all quite a bit larger. They are all 70-meter antennas. So if you look at the screen on the far right, where it shows you that picture, the 70-meter antenna, that picture, I think there's two pictures, right? Is it cycling through the day and night pictures? Sometimes it does, sometimes it doesn't. But those two pictures, they're both of antenna number 14 in California. And the reason they're that antenna, because we can go out there and take nice pictures of it easily. We can drive there and do it. So, but that picture is there just to show you scale. So look at the upper right-hand corner of that picture where it says 70-meter antenna. Taken on a separate day, this was a close-up of the center of the antenna. You guys see the red circle? And you see that black arrow, that squiggle the black arrow is pointing at? You can probably tell from here, but that's a guy standing there, right? And then right in front of him is another dude sitting there. So in that red circle, there's two people there. 70 meters is almost exactly 230 feet. So that's most of the size of a football field from one edge of that antenna to the next. So they're absolutely monstrous. The smaller ones that you see in the diagram, all the other small ones are 34 meters, so they're all the same size. So, and the thing is, the bigger the dish, the weaker the signal we can detect. So that's kind of what's going on. A couple other things to notice. Downstairs, you'll see on that clock, that panel anyway, below the antenna picture, where it says UTC. You guys all scope that out there? So that stands for Universal Time Coordinated. It's effectively the same thing as Greenwich Mean Time. And we use that as our timekeeping standard because all those tracking stations are in different time zones. And rather than having to worry about what time it is where, everybody dials into that, so we're all talking the same time language, basically what that is. So the first number, 11, is the day of the year. So it's the 11th day of the year, 22nd hour, 41st minute, 25th second, blah, blah, blah. So, and of course, you remember that's not the time here. Greenwich Mean Time, that happens to run through England, right before the prime meridian is. So that's really what it is. It's atomic time. That's really what it actually is. It's atomic time at the prime meridian. Whereas Greenwich Mean Time as a standard of time, in quotes, right? That's actually based on the movement of the stars. So UTC is actually more accurate because it's atomic clock based, so it's better for navigation and stuff like that. But since UTC's kind of adaptation by this spacefaring communities around the world, they've actually had to add seconds to it to keep it in sync with the rest of the movements. So we don't get off. And then the numbers below UTC are actually cool and fun numbers for us. Cassini plunge, so you'll notice it's counting backwards, right? It's 247 days away from when we actually will splash Cassini into the atmosphere of Saturn. That's September 15th. So that will effectively end the mission. So we do that on purpose. Spacecraft is running out of propellant, and we don't want to risk losing control of it and then having it perhaps smack into one of those very icy moons that could potentially harbor life. So this was never designed, Cassini was never designed to land anywhere, so it didn't go through the same decontamination procedures that a rover would. So it could still, not likely, but it could still harbor Earth bacteria. It does have the radioactive isotopes on it. We don't want to introduce those into any place that might, be pristine. So when we vaporize it, when it goes through the Saturn atmosphere, it will vaporize the spacecraft as it gets deeper and deeper. So that'll be the end of her on September 15th. And then below that, the JOI part of Juno, you guys might remember, is a spacecraft currently orbiting Jupiter. JOI stands for Jupiter Orbit Insertion. So that's the day it went into orbit. So you'll see that's 189 days ago, since it's got the plus in front of it. That was actually 4th of July, that evening. So that was kind of cool. All right, so this is a nice quiet day. This is what we like to see. Keeping it real down here, right? That chart that's on the left shows you a lot of the spacecraft we communicate with often. That's not all of them. Okay. But it's color-coded. Don't worry about the colors. That's for a whole different schedule they use. So that's really for their benefit rather than ours. But above each box, you'll see that little white bar that's got the name of the spacecraft. That stuff in the boxes is the data coming back from the spacecraft. If it's moving, it's live, coming back right now. So it doesn't look like much. You know, actually our spacecraft transmit in pretty much pure binary code. So when the data gets back here, it's compiled into these little packets, they're called. It's a lot like when you take pictures with a digital camera, and then let's say when you used to dump them on your computer, and if you weren't looking at the photograph itself or the thumbnail, the computer would say this is picture number blah, blah, blah, blah. Right? It always has some like code to it. That's basically what that is. It's like that code. It's longer. There's more data in there for us. But it basically helps us sort it out.
And they
like,
always use those same colors.
Always use, yeah, each spacecraft is assigned a color. Yeah. And that's for a scheduling tool they use. So they basically have this chart that they use for scheduling. But so yeah, so basically think about it. Like the Curiosity rover has 10 science instruments on board. We never download all 10 at once, but there's a good chance we might download 6. We're gonna be out here. Melissa, we're gonna be out of here in just a second. So where are you right now? But anyway, once it gets compiled into that, that helps us sort it out so we know what instrument on the robot it came from. Okay? All right, guys, we got to hustle on out of here. So take your last shots before we go. All right, my friends, follow me. Actually, we're coming out.
Şimdi uzay araçlarının yapıldığı yere gidiyoruz. You do this every day?
Yeah, every day.
Yeah.
Sometimes twice. Most days, twice.
Yeah.
It's fun. I love it.
A lot of visitors.
A lot of visitors, yeah. We probably do, I don't know the actual numbers, Melissa would know, but I think we do something close to 30,000 a year. It's a lot. It's fun. Keeps us on our toes. Alright, looks like we're all here. Alright, folks, follow me. So where'd you come in from today? Where'd you guys come in from? Turkey? No way, cool.
I am from Turkey.
Nice. How long are you here?
14 years.
14 years, okay,
Yeah.
cool.
Yeah, I'm an astrophysicist.
Okay, where?
Yeah.
Here, in the States?
Yeah, yeah.
Where do you work?
In SMC?
Oh, okay, cool.
Yeah.
You live nearby, or?
Yeah, yeah.
Okay, cool. Very good. How was traffic getting here?
It was not bad, not bad.
The rain that let up
Yeah.
by then, right?
Last time it was bad, but this time good.
Where'd you come from?
Santa Monica?
Oh, Santa Monica?
Yeah.
It's getting home that's going to be trouble.
Yeah.
That's always the problem, getting out of here. Getting to the west side, going east, that's always really tough. I live close, thank God. So you've been before? Come to the lab before?
Yeah, yeah.
Oh, cool. I would suggest if you can, come back in like a year. The rover would be like...
I am always here.
A year a lot? Cool.
Öğleden sonra 3'e geliyor saat.
So you've been back home lately?
No, not for 3 years.
3 years?
Yeah.
What's the weather like there this time of year?
Almost, but right now it is snow.
Snow?
Yeah, snow.
So pretty chilly. That's cool. Do you still have a lot of family back home?
Yeah. Where are you from originally?
Originally, actually from Delaware.
Oh.
Yeah. My family's Italian. But my dad's second generation, so.
You look like Turkish, so. Because Italian and Turkish are Mediterranean. So.
Yeah, right. We all kind of look the same, right?
Yeah, we look same, yeah.
And my mom, she's kind of European, I guess. She's like, I got light red hair. That's funny. So my brother, he looks a lot more like my dad. He's got the darker hair, a little darker features.
but we both got my mother's really light skin. It's terrible because it gets freckly and it suffers really easy. Alrighty folks, just want to get your attention real quick. We're just going to head into this building behind me. This is where we build the spacecraft. I just have a couple favors to ask. We have to go up some stairs. So they're kind of narrow, you know, if there's employees coming down. So I'm just going to ask if you would be in a single file line. That'd be awesome. And if you would be so kind as to use your really quiet footsteps, because it's an old building. If you pound on the steps, they can hear it in the entire building. Okay, that's all. Follow me folks. Thanks. Watch out for the flying golf carts.
Sorry.
Yeah, they're like the last people to touch, right? You know, like they have to be careful because if they do something wrong, it's over.
Burası uzay araçlarının yapıldığı yer.
When it's in space, everybody can fix it.
5 dakikaya turumuz bitiyor.
Alright guys, can y'all hear me okay? I'll stay down here. I don't want to talk over them too badly either. We try to share this gallery as acoustically. It's a nightmare, but we'll do our best.
You know which spacecraft we're working on now?
Yeah, I'll tell you all about it, yeah. So, if you've not been here before, welcome to our spacecraft assembly facility. This is where we actually put these things together. We do have the capability here at the lab to build just about all the parts necessary for our spacecraft. We rarely do that.
Uzay mekiklerinin
Simply
yapıldığı
because
yer.
timelines don't allow it. In some cases, we can't build the parts. So even in a mission, a spacecraft that we would consider in-house, we might be building 30%, and then we would send the rest of the parts out to other companies around the country, sometimes around the world.
But assembly takes part here.
But yeah, so assembly takes place here. So all those parts eventually get here, either from the lab itself or from these external sources, and we need some place to put the thing together. So that's what this room is all about. It's basically a big workshop where we do all the final assembly and testing.
I assume if you're working with titanium, that's
O burada değil, Ohio'da.
We're starting to work with that on our own here, yeah. So some of that, but like the titanium parts on Curiosity actually came from Lightspeed, which is a company that manufactures mountain bikes back in Tennessee. And they were funny because we checked their website the day after we landed. They had this big splash page about our titanium on Mars. They were so jazzed. It was great.
I worked with Beryllium at, I've been working on the Beryllium for part of the space lab.
Oh, cool.